पेट्रोल डस्टर ಇಲ್ಲ ಸ್ವಲ್ಪ ಕಟ್ಬಿಡಿ ಇದೆ. Good morning, students. Can you hear me? Loud and clear? Are you able to hear me? So first, before starting the chapter, we have to make sure that everybody is able to hear everything. So that is the important thing. Now, today we are going to take off from where we have left last class. In the previous class, we have discussed about the Coulomb's law. So where we are going to find out the expression for the force between the 2 point charges. Again, I am going to draw the diagram. There are 2 point charges, Q1 and Q2. The distance of separation between them is represented as R. Then the charge Q2 will exert a force on the charge Q1. So therefore, let us imagine that we are interested in finding out the force experienced by the charge Q1 only. So which is exerted by the Q2. According to the Coulomb's law, the magnitude of the force is given by F is equal to 1 by 4 pi epsilon naught into Q1 Q2 divided by R square. So this is the magnitude. And direction of the force, it depends on the polarity of the two charges, not on the single charge. It depends on the polarity of both the charges. If they are both positive or both negative, that means in general they are like charges, then there is a force of repulsion. The charge Q1 will be repelled away from the charge Q2. So therefore, it will be along this direction, along the lines joining the 2 point charges and also away from the other charge, force of repulsion, if there are like charges. If they are unlike charges, then this will be force of attraction here. Either Q1 may be positive or negative, but Q2 should be of other kind. When there is a force of attraction, again the force will be along the same line, but it will be towards the other charge. So this is how we have understood the Coulomb's law for only 2 charges here. Now what we are going to find out is the what if instead of only 2 charges, if there are number of charges, many charges are present, then what happens to the force acting on the charge Q1 here? Imagine that. So there will be another charge somewhere here, Q3, one more charge somewhere here, Q4, other charge Q5, like this. So there is a multiple charges are present here. When multiple charges are present, then what happens? Can we use the Coulomb's law in this case also? That's the question. What do you think? Of course, we can use the Coulomb's law for any number of charges to find out the force on a given charge. Here we are trying to find out the expression for the force experienced by the Q1 only. Not interested on the force acting on the other charges. We are interested on finding out the force acting on the charge Q1 only. And also here, the condition that must be satisfied is that, so these charges must be point charges. Multiple charges may be present. As long as they are point charges, we can definitely apply the Coulomb's law. So how we are going to apply the Coulomb's law? That's the question. Here you might have studied the principle of superposition in the last year itself. Principle of superposition. According to which, if you need to find out the sum of many things, if you want a net quantity of something, I am not going to say force itself, net quantity. It could be anything. This quantity could be anything. Force, it may be force, it may be displacement, or it may be something else. Energy, anything else. So therefore, obviously, when we consider the net quantity on a particular thing, so then it should be equal to the sum of the individual quantities. Net must be equal to sum of the individual things. The same principle has been already used in the previous year while discussing the oscillations and also waves. But here we are going to use the principle of superposition in case of the force. Electrostatic force, but still it is a force. Force is a vector quantity. So therefore, we cannot take simple addition here. Simple addition, arithmetic addition cannot be used for the vectors. For vectors, it should be vector addition or vector mathematics. Vector addition, vector sum, everything, vector quantities. That means we cannot only consider the magnitude, we have to consider the direction also. Let us see how we can use the principle of superposition in case of finding out the net force acting on the given charge due to the system of charges. So this is the introduction to the concept here. Now I am going to actually derive an expression for the net force. But when we are going to consider the net force, then we are going to imagine the simplest case. So if we consider the multiple charges, which is more than 2 charges, then the simplest one is the system of 3 charges. So we are not going to take many charges and get things complicated. We are going to keep the things very simple here. So therefore, we are going to consider a system of 3 charges only here. So one is represented as Q1, so which is the charge of interest here. So Q1 is the charge of interest. I am going to draw it somewhere here. So Q1 will be the given charge. So that is the charge under consideration. Look at it, that charge Q1. So in the vicinity of Q1 there will be many charges. But for simplicity, we are going to consider 2 other different charges. You can draw those charges anywhere you can. It is not like that you have to draw the charges here itself. Only this specific position, that specific position, not like that. We can draw anywhere. You can draw the other 2 charges somewhere above the Q1 or below the Q1, to the left of the Q1, to the right of the Q1, one above, one below, like that. It could be anywhere. But we have to understand the concept perfectly. First, I am going to consider, it will be depending on the availability of the space in your exam paper or the answer paper here. So therefore, if I have chosen the value Q1 here, so then I have space everywhere around it. So therefore, I have a freedom to draw the charges everywhere. So but I am going to consider a charge Q2 somewhere here. Q2 will be somewhere here. And again, remember that for our convenience, we are going to assume that all these charges are positive. You can choose the negative charges also, but accordingly you have to make some difference, changes here. So that's it. But now we are going to consider the charge Q2, which is placed at that position, and the distance of the charge Q2 from the Q1. This distance. So that will be represented as again R itself. But here the problem is that there is another distance also, which is representing the distance of the charge Q1 from the charge Q3, which is not yet represented here. So therefore, we have to be specific about mentioning the value of R. So this R is the distance between Q1 and Q2. So therefore, I am going to put the subscript R12, which is indicating that it is the distance from Q1, distance of Q1 from Q2 here. That means this is the reference point. If we need to find out the position of the Q1 with respect to Q2, this is the reference point. So therefore, the direction in which we have to move from the Q2 to reach the Q1 is represented by the arrow. R12 being a vector, so therefore this is the direction of R12. Similarly, other charge Q3, it will be considered here. You can consider it somewhere here also, does not make any difference. You can consider it here. Diagram has to be drawn as the space is available here. We cannot by heart these things. You should not by heart these things. So look at this. Again, similarly, we are going to draw this line to join these 2 points here. Again, the distance of separation between the Q1 and the Q3, it will be represented as R13, distance of the charge 1 from the charge 3. So therefore, R13 being a vector. In order to reach Q1 from the Q3, we have to move along this direction. So this is the direction of R13. Both are vectors here. And now, we are going to consider the force acting on the Q1 here. First, we have to remember that when we consider the principle of superposition, so each charge in the system, it will be exerting the same force on the Q1 even when all the charges are absent here. In all cases, it will be the same. The force exerted by the Q2 on the Q1 is same whether Q3 is present or not. If you keep the Q3, the Q2 will exert the same force. If you remove the Q3, the Q2 will exert the same force on the Q1 here. So this presence of the other charges are not affecting the force exerted by the charge Q2 on the charge Q1 here. So therefore, we can apply the Coulomb's law to find out the force acting on the Q1 due to the Q2 only. So which is given by F1. So this F1 is representing the magnitude of the force on Q1 due to Q2 alone. Imagining that Q3 is not present. Q2 is not present at all. So Q3 is not present at all. Only Q2 is present. So now, according to the Coulomb's law, the force on Q1 due to the Q2 is equal to a proportionality constant, considering the charges are placed in a free space. Then the product of the magnitude of the two charges, not considering the polarities. We should not consider the polarities while considering the magnitudes. So therefore, product of these two, which will be equal to Q1 into Q2 divided by the square of the distance of separation between the two charges, which is represented as R12 square. So this is the magnitude of the force F1 on Q1 due to the Q2. Now, force being a vector quantity, so therefore we also need to show the direction of the force F1 here. So what is the direction of the force 1? Mathematically it is simple. So we can just draw an arrow above the F1 and we can place on the right hand side, we can multiply the magnitude of the force F1 with a unit vector representing the direction of the R12, which is R12 cap. So this is how we are going to represent it mathematically. But actually, what is the direction of F1 in that diagram? So that is important. Mathematical expression is important, but more than that, understanding the concept is important, where we can find out the actual direction of the F1 here. Since these two charges are positive, as we have imagined, so therefore there is a force of repulsion, and also we are interested in the force acting on the Q1 only, not on the Q2, by the Q1, only force on Q1 due to the Q2. So therefore, here, so it will be force of repulsion, and also along this line, we can extend this line. So this is the direction of the force F1 here. In diagram, so this is the direction of the force F1. And also remember that the length of this arrow should be equal to the magnitude of the force F1. But we are generally expressing that, so therefore we have to place some length here. So which is, we can imagine that, which is representing this magnitude of F1. Similarly, we can also find out the force on the same charge due to the third charge, Q3. Force on Q1 due to the Q3, imagining that now Q2 is not present. And that force is represented as F2. The force on the Q1, for our convenience, I will write like this. So F12, F12. More specific, because this is the force on the charge 1 due to the charge 2, so this is the force on charge 1 due to the charge 3, in order to avoid the confusion. So now, what is the value of F13? Again, we are going to consider the magnitude. It is equal to a proportionality constant multiplied with the product of magnitude of the two charges, which are these two, which is Q1. Now it is Q3 divided by the square of the distance between Q1 and Q3, which is R13 whole square. Vector notation, place an arrow on the force on the left hand side and multiply the right hand side with the unit vector representing the direction of R13. Since there is a positive charges, both are positive charges, force of repulsion is present, therefore it will be same as that of force is in the same direction as that of R13. So therefore it will be R13. Yeah. If it is opposite, so then you have to place a negative sign. So that is how we are going to place the positive or the negative sign to the force. We are not going to consider the magnitude of the charges here. Instead of that, we are going to place the positive or negative sign to the force, indicating that whether the force is in the direction of R13 or opposite it. If F13 is in the direction of R13, so then the force is treated to be positive. This unit vector is treated to be positive. If F13 is in a direction opposite to that of R13, so then this is negative. R13 minus R13, unit vector R13 will be multiplied here. So that is the case here. When we are trying to find out the direction of the force, even remember that polarity of the charges should not be placed in the equation. But depending on the polarity itself, the direction of the unit vector determines the direction of force. So that should be remembered. Now, again we have to represent the vector F13 in the diagram. So therefore, again, Q1 and Q3 are both imagined to be positive charges. Therefore, it will be along this line. So I am going to keep it little shorter here, just to show that, this F12. This F12 and F13 are not equal. They are not necessarily equal, because the distance may not be same and these two charges may not be equal. So therefore, these forces F13 and F12 may not be equal. So therefore, it is better to draw the two arrows of different lengths here. You can make this larger, this shorter, doesn't make any difference, but you have to remember that they are not equal. You are not drawing the diagram, so you are not drawing any picture here. It is not an arts class. Okay, so therefore, you have to remember the significance of everything. Now, since we have obtained all the individual forces which are acting on the charge Q1, so then what is the net force? That's the question, where we can apply principle of superposition. If we need to find out the net force acting on the charge Q1, which is represented as vector F1, representing the total force acting on the charge Q1 due to all the charges around it, which is Q2 and Q3 here. And according to the principle of superposition, the net force must be equal to the sum of the forces acting on the given charge, which is Q1, due to the charges present in the system, so that they are present all alone here. So that means we have to add the individual forces, so which is represented as F12 and vector F12 and vector F13. So for net force and on the Q1 will be equal to F12 plus vector F13. So this is the mathematical expression. Don't get fooled by the equation here, because here we need to take the vector sum. That means we need to take the sum of the two vectors here. Again, vector rules has to be followed. How do you show? So this equation in the diagram, what do you do to add the two vectors? Right, we are going to use the parallelogram law of vector addition. Here in the diagram, we have to make use of the parallelogram law of vector addition. So that means here from F12, we have to draw a line which is parallel to the F13 and should be equal to the length of the F13. Roughly I am drawing it. And from this point, we have to draw a line which is parallel to F12, and also it should be of equal length as that of the F12 here. So hence we have constructed a parallelogram. So roughly it will be representing a parallelogram. Now the sum of these two vectors F12 and F13, so that will be determined by the diagonal of the parallelogram starting from the common origin. The common origin is this one, where both F12 and F13 are starting. They are beginning from this point. So this is the common origin of these two vectors. From the same point, we have to draw the diagonal. So that diagonal is this one. This diagonal is representing the vector sum of the F12 and F13, which is represented as vector F1. It is representing vector net force acting on the charge Q1 due to the charge Q2 and Q3, both in magnitude and also direction. Net force. So that's the condition. So now we can substitute the value of these two mathematical for a mathematical representation. So therefore it will be equal to 1 divided by 4 pi epsilon naught Q1 Q3. Sorry, Q1 Q2 divided by R12 square into R12 cap plus 1 by 4 pi epsilon naught. Second one, Q1 Q3 divided by R13 square into R13 cap. If another charge is present, then we can add it plus 1 by 4 pi epsilon naught into this charge under consideration Q1 into the other charge, fourth charge Q4 divided by square of the distance of that charge from the Q1, which is R14 square into R14 cap. Like that we can add any number of charges. We can go on adding the charges here. So first, in order to simplify that, if large number of charges are present, we have considered the multiple charges, simplest case of the multiple charges where only 3 charges were present. If there are large number of charges, so then what happens? The mathematical representation will be easy, but actual addition will become more and more difficult. You have to add that vector. So for vector addition become more complicated here. But mathematical representation is simple. We are going to take the help of summation signs here. So where we can see that 1 divided by 4 pi epsilon naught is common in all the terms. Both terms in this case, if there are number of charges, so then it will be common in all the terms. So therefore it will be written outside the bracket. 1 divided by the reciprocal of the 4 pi epsilon naught. reciprocal of the 4 pi epsilon naught. And also we can see that in every term the q1 is common. So therefore it can also be taken outside, common term q1 divided by 4 pi epsilon naught. Then other terms will come. Summation of I equal to 1 already taken here. 2. The first term starts with the 2, 3 and like that. 2 to n or infinity, or you can just ignore this. You can just put the summation sign. The remaining term. So when I equal to 2, this term, when I is equal to 3, this term. So like that. So we are going to represent it as a qi. q1 is taken outside. Only so these terms are present. So for qi divided by, again the distance is 1 is common everywhere. This 2, 3 is changing to I. So for it will be represented as r1i square. Similarly, unit vector is also represented as r1i cap. So this is the general expression for, mathematical expression for deriving the net force due to number of or multiple charges. Net force on a given charge due to multiple charges. I hope this thing is clear. And now, are you good? Have you understood the concept? Because it will be more useful in solving the numerical problems. So whenever we are going to consider the shape of a square, where at the corners of a square there are charges are present, which is nothing but the system of 4 charges. Same thing, it should be extended. The mathematical expression has nothing to do with the answer. We have to use this method here. What is the angle between these two forces and these two forces? In which angle? With respect to this force, the other force is acting. The third force, with respect to the first force, what is the angle? So everything should be used here. The vector addition, that diagrammatical form should be used here. Not this one. This is a mathematical expression. You cannot multiply like this and add them here. So direction is also important. Just simply you cannot add the magnitudes. Direction should be considered. So we will discuss that in later classes with the example of some square or a triangle. We are going to solve it. Remember it. So, but for the time being, so we can assume that. So this is the mathematical form. That's the actual form of finding out the net force acting on a charge due to multiple charges. This is the equation. I think we can move on to the next concept, which is the electric field. Again, when we consider the electric field, then the question arises in our mind. What is the field? In the last year also you have studied about a field, which was the gravitational field. This is also similar to that. Look at this chalk piece. This chalk piece is experiencing the gravitational force. But as I leave the chalk piece, it will start to fall, because it will start to experience the force. As long as I am holding the charge, it is not moving because I am compensating the force here. But once I release it, so it will start to move downwards due to the force experienced by it. This force which is experienced by the chalk, so that is due to the something which is already present everywhere, which is not visible to our eye. Naked eye cannot see that, but that something is present. So that is known as a field, which is known as the effect of the gravity. Gravitational field is known as effect of the gravity which is present around any object here. The chalk piece also has its own gravitational field, but compared to the gravitational field due to the earth, we are unable to detect the gravitational field due to this chalk piece because of its smaller size. But still, it has its own gravitational field. Similar to that, the charges will also have its own field here. Electric field in general words, in general terms, it can be described as it is the area around a given charge. I will represent it as a capital A. The area or space around the given charge, three-dimensionally speaking, it is the space around. So three-dimensional space around the given charge where effect of this charge can be felt by another charge. This effect due to this charge will be felt by the another charge only. If we need to find out whether the electric field is present due to the given charge, what we have to do is we have to test. How do we test that? We are going to take another charge. We are going to place it somewhere here, small q. If this charge experiences the force, electrostatic force, then it is obvious that the electric field is present. So therefore, the charge which is used for testing the presence of the electric field due to the charge capital Q. So therefore, this charge is known as test charge. Test charge. It is not of importance while discussing the electric field. It is not that of that importance here. It is less important. Generally speaking, it is not required at all. It is only used for testing the presence of the electric field due to this charge. And this is the charge which is creating the electric field. It is the source of the electric field. So for this charge is known as a source charge. In electric field, the source charge is important. Test charge is used only for testing the presence of the electric field due to the source charge. So that's all. So therefore, usually what we do is we are going to take a very small test charge, because we know that according to the Coulomb's law, both the charges will exert equal and opposite force on each other. So therefore, we have to introduce the test charge, which is so small that the force due to the test charge on the source charge should not be able to alter it with a greater extent. A very small change or negligible change, negligible force can be created by the test charge if we make the test charge itself very small. So that's the condition. Otherwise, because of this test charge, the source charge will start to move. So for the system, the distance will vary. So that will be the problem. Field will change. So that is the one reason why we are going to keep the test charge very small. And one more thing is that we can keep the source charge fixed at its position due to some unspecified forces. It should be kept here. Here itself, whatever may be the value of test charge, the source charge should not move from its position. We have to do something. We can glue it. We can put a nail on it. Something. But it has to keep fixed at its position. So that is how we are going to consider the source charge. So that is the general way of expressing it. Source charge and the test charge. So now, we are going to consider the mathematical expression for the electric field due to a point charge, and also in general, how do we express the electric field? First, we have to again consider the Coulomb's law. So this definition is based on the Coulomb's law itself. If there are two charges given by capital Q and small q separated by a distance r, imagine that, and both are being a positive charges spaced in a free space, distance of the test charge from the source charge, which is represented as r, then the force on q is represented as F, and that will be is equal to 1 by 4 pi epsilon naught into product of magnitude of the two charges, capital Q into small q, divided by square of the distance of separation, magnitude. So this is the fix. And now, if this is the source charge and it is of interest, and this is the point P where we need to find out the force on the charge Q here, small q. And if you are go on changing the value of Q, the force will change. If you change the Q, F will also change. If you increase the Q, F increases. If you decrease the Q, F decreases. So therefore, we are unable to find out the actual effect of the capital Q. So therefore, the expression for the force or the concept of the force is not useful to find out the actual effect of the capital Q at this position P, where the small p is placed here. So therefore, it is necessary to introduce another concept which is independent of the charge used for testing the presence of the electrostatic force. So that is known as the electric field. And how do we express the electric field? In general, if we consider the electric field at a position R, where R is the position vector, we do not know. So like in this case, here we are not mentioning the location of the source charge, which is the source of the electric field, we do not know, but it is present here. In that case, at a given position R, the electric field is equal to the electrostatic force experienced at that point, so which is represented as F of R. The force at that point, like this, at position R, the force is represented as F of R, function of R, divided by the test charge. That's the expression here. That's the expression, general expression for the electric field at a given point. Remember that we are going to define the electric field at a given point here. At this point, the term electric field has no complete meaning. Always we have to mention that electric field at a point. At this particular point, electric field due to the source charge capital Q will be, according to this equation, it will be represented as electric field will be equal to F divided by Q, which should be equal to, substituting the value of F from this equation, it will be equal to 1 divided by 4 by epsilon naught into Q divided by R square. Now look at this equation, right hand side of the expression for the electric field. It is independent of the test charge. Whatever may be the value of the test charge, the electric field at that given point P does not change. If you place, instead of Q, small q, we are going to place Q1, the field is going to remain the same. Field is not going to change at all. Force, of course, changes. Net force changes. The force on the Q1 is different from the force acting on the Q. But electric field is same, whether it is small q or Q1 or Q2 or minus Q1 or minus Q2, anything. But field remains the same. Force may change. The direction of the force may also change depending upon the polarity of the test charge. Usually we are going to place a small test charge only. So this is the expression, method, general expression and expression for the electric field at a given point. The direction I will come later. First we are going to define the electric field. What is the definition of the electric field? Which is based on this equation only. Definition of electric field. This equation or general, in general, this equation. How do we define the electric field? That's the question. Here, again, since we are using the help of, with the help of this equation, we are defining the E. Let us imagine that Q is equal to plus 1 coulomb. Plus 1 coulomb, which is known as unit positive charge. When test charge is unit positive charge, remember that this unit positive charge is much larger charge. It requires 6.25 to 10 raised to plus 18 number of positrons to consist this amount of charge. It is a very large charge, therefore force exerted by the test charge and the source charge, if it is equal to plus 1 plus 1 coulomb, it is huge. But we are imagining it, so that we can imagine something which is convenient to us, mathematically convenient to us. So therefore we are going to assume that, so this is unit positive charge. In that case, so when Q is unit positive charge, so this equation or this equation, how it can be represented? It will be is equal to E is equal to F divided by 1, which is equal to F. So that's the definition. This expression is definition here. So when E is equal to F and Q is equal to plus 1 coulomb. So therefore we can easily define, we can express the definition of the electric field based on this expression. Electric field at a point is equal to the force experienced by a unit positive charge placed at that point. So that's the definition of the electric field. Very simple. We can define the electric field at a given point only. So for electric, from in this diagram, look at this diagram. Electric field at this point due to Q, electric field at this point P is equal to the force experienced by the unit positive charge plus 1 coulomb, which is placed at this position. So that's the definition of the electric field. Simple definition. Electric field at a point is equal to the electrostatic force experienced by a unit positive charge placed at that point. That's the definition. Are you getting it? Okay. Then, now, from the same expression, we are going to, again, a new concept or a new physical quantity has been introduced. So, therefore, we need to know its SI unit. What is the SI unit for measuring the electric field? Look at the expression. We know the force and also charge. Electric field is depending on force and charge. Therefore, what is the SI unit for measuring the force? Whatever kind of force may be, it may be, but it is force. Therefore, it is measured in Newton. And at the denominator, we have charge, which is measured in coulomb. So, for Newton per coulomb, it is SI unit for measuring the electric field. In the next class, you will also find out that the electric field is also measured in volt per meter. It is a derived unit. So this is a derived physical quantity. Therefore, obviously, unit could be written in any terms here. Instead of Newton, you can also introduce the joules. So it does not make any difference. But question is, so we have to understand the concept. So if you use this equation, it will be represented as Newton per coulomb. If you use another equation for the potential difference, so then in this equation, they are one and the same. They are same. But for now, remember this. It is measured in Newton per coulomb. So this is also commonly used SI unit for measuring the electric field. Both are used accordingly. Whether the electric field is represented in terms of the force and the charge, this will be used. If electric field is expressed in terms of the potential difference or the voltage, so then this unit will be used. They mean the same thing. Both are same. But remember the SI unit. And now the important thing. It is the direction of the electric field. What is the direction of the electric field? How do you find out the direction of the electric field? First, we are going to consider the condition, this condition itself. I will try here. Here there is a source charge, capital Q. And then here there will be test charge, which is represented as small q. And remember that test charge is always stated to be positive. It is very small but positive charge. We are not going to test the presence of the electric field due to the capital Q with the help of negative charge. We do not do that. Why we do not do that? It is a convention. It is a practice which has been carried out for very long time here. If you want to test something, we are going to use it positive charge itself. So therefore, test charge will never be negative. We are choosing it. So therefore, we are going to choose it to be positive. So therefore, test charge is positive. Now, if we need to find out the direction of the electric field, then of course it will be depending on the polarity of the source charge, because this is always positive. Let us draw the point P. This is the point P where we need to find out the electric field due to the source charge Q. And the distance of the point P from the source charge capital Q is represented as, in general, R. And in order to reach the point P from the Q, this is the reference point. From here we have to move towards the Q. P. So therefore we have to move this distance along this direction. Therefore it's a vector. The direction of R is along this direction. Now remember this. Now if imagine that Q is positive. First we are going to consider the positive charge itself. Source charge is a positive charge. Then what is the direction of electric field at this point P? Remember that. Again, carefully note that the electric field that we are going to represent is at this point, not here. It is the electric field at this particular point itself. Source is this charge, but field is present at this point. It is present everywhere, but we are trying to find out the electric field at this particular point itself. So therefore, the vector has to be drawn here, which is representing the electric field. If I am going to represent the electric field as E at this particular point, in order to find out the electric field, I need to find out the force. What is the direction of the force here? Which is acting on the Q, small q, due to the plus Q. Again, force of repulsion, like charges, force of repulsion. Therefore, it will be along this line, but away from the Q. Therefore, it will be the direction of the electric field. So, this is the direction of the electric field. So, this is the direction of the electrostatic force. From at this point, it will be directed away from the positive charge. And now look at this, at this expression here, E is equal to F by Q. So, force is a vector, charge is a scalar. And also it is a positive charge, but we need not to consider the polarity here. Since charge is a scalar and only the vector on the right hand side is the force, therefore electric field must be in the direction of the force itself. So therefore, the direction of the electric force due to the positive charge at point P is same as that of the F. Same as that of the F. Remember that. Direction is same as that of the F. I am not concluding this. So this is one point. And also here, the magnitude of the E, it is not necessarily equal to F. So therefore we have to draw the another arrow itself. It may be larger than F or it may be shorter than F. Depends. Here I will draw electric field since Q is very small. Less than 1, very small. So therefore, I will imagine that the force is smaller in magnitude, field is larger in magnitude, but they are in the same direction according to this expression. So this is about the positive charge. We will make the conclusion later, general conclusion for finding out the electric field later after considering the negative charge. Now we are going to consider a source charge which is negative 1. And we represent it as a Q itself, but it is a negative charge, which is located here. And at this particular point, say I will represent it as a P dash, different point, which is again at the same distance. Distance is the same, which is represented as R. Again, same. So then, direction of R, it will be from P to Q to point P, charge Q to point P, and it is a vector. And now, in order to find out the electric field at P due to the capital Q, you have to place again positive charge, test charge, positive test charge plus Q. And now what is the direction of the force? So this is positive, other one is negative. Source charge is negative, test charge is always as usual is positive. So therefore there is a force of attraction. So for electrostatic force acting on the Q which is placed at the P dash, it will be directed towards the negative charge. So therefore this is the direction of the force. I will write it as a F dash vector and this force F dash is opposite to the position vector. So for in this form if you have to write the expression for the F dash, how do you write this? F dash vector F dash must is equal to 1 by 4 pi epsilon naught capital Q. Now polarity of the negative charge, you should not place the polarity of the negative charge, it is immaterial, should place the magnitude only into magnitude of the test charge Q divided by the square of the distance of separation, which is again represented as R itself. It will be equal to R square into the unit vector which is representing the direction of the F1 dash, which is opposite to the R dash. Sorry, which is opposite to the R. Therefore, in order to represent that, it is F1 dash is opposite to the unit vector R dash, the negative sign should be here. That negative sign is not because of this, the negative sign of the capital P. It is not because of that. It is because it is opposite to the R. This was the reference point. We are moving away from the reference point, but the force is directed towards the reference point. So that's why there is negative sign. So that is what I have mentioned earlier. But here, again according to this equation, the charge is again scalar quantity. The force is a vector quantity. So for electric field on the left hand side, which is a vector, it should be having the direction same as that of the vector on the other side, which is only vector on the right hand side is the force. Therefore, what is the direction of the electric field? Same that as that of F1 F dash. Therefore, I will consider E dash, electric field at E dash due to the minus Q at this particular point E dash. It will be represented as E dash. Magnitude is smaller than F dash. Convention or some assumptions. Okay. That's all. So therefore, this is the direction. Okay. Have you seen the direction? In order to find out the direction of the electric field, we have chosen a unit positive charge. But we know that electric field is independent of the test charge. So therefore, we do not need these test charges. We are going to take it out. Force, we do not need. To understand the direction of the field, we have made all this assumption. But generalizing, for making the generalization, we do not need this charge. We need this point. We do not need this force. We have already obtained the direction of the field. If there is a test charge, this will be the direction of the field. If there is a test charge, this will be the direction of the field. We are going to take it out. We are going to keep only the direction of the electric field or everything. I will remove it. Now, what is the generalization? Conclusion, the final part, to find out the direction of the electric field. What is the direction of the electric field? It depends on the polarity of the charge. If the source charge is positive, the electric field at a given point is always away from the source charge. If source charge is negative, then direction of the electric field at a given point is always towards the source charge. Electric field is away from the positive charge. Away from positive charge, and electric field will be always towards negative charge. That's the generalization. Whenever you find the given point, if you need to find the electric field at that particular point due to some positive charge, it will be away from it. Simple case, I will consider a rectangle. Here there is a positive charge which is represented as plus q1. At this position there is a negative charge which is represented as minus q2, and here there will be another charge which is represented as q3. Imagine that this is also positive charge, and we need to find out the net electric field at this particular point. So net electric field means we need to find out the electric field, direction of the electric field at the fourth corner. So then what is the direction of the electric field at this particular point due to the q1? It will be due to the q1, it will be like this. So this is the direction of electric field away from the positive charge, and this is also positive charge. So at this point, electric field due to the q3, it will be again away from the q3, e3. That's the direction of e3. But when we consider the same point, the electric field due to the negative charge, it will be along this direction. So this will be the direction of e2. So this is how we can find out the direction of the electric field, depending on whether it is a positive charge or negative charge. In general, remember that the electric field at a point is always away from the positive charge, and it is always towards the negative charge at a given point. Source charge indicates the direction of the electric field. That is how we are going to generalize the direction of the electric field. So there is one more concept which should be discussed. I think we will discuss in the next later classes. So where we are going to find out the actual value for the electric field at this particular point due to the system of charges. Remember that it is very easy. Once you have discussed the expression for the force on a charge due to multiple charges, the same derivation is also used for the electric field at a point due to multiple or system of charges. But only difference is that instead of force, we are going to use the expression for the electric field. In that case, we have used a given charge q1. Here we are going to take this charge as a test charge, and q1 will disappear in the final expression. I think today this much will be enough. Hope you have understood the concept clearly. If you have any doubts, please make some comments here so that we can improve in the next class. If you have any doubts, I already told you, share it in the WhatsApp group. The YouTube comments, we are unable to read it because of the lack of time. But in WhatsApp group, we will read your questions. And at the beginning of the previous class, we will discuss those problems. So then we will continue with the topics. So thank you.